Good afternoon, and I'm very happy to be here. What I want to talk about today is zonal ECUs in software-defined vehicles, require a system-level framework. And I take that for safe and secure communication. It's as important as the safe and secure OTA update. So, let me explain what is going on, here. The agenda quickly, I'll do an introduction, zonal architecture. I take Ethernet as an example, why you should, probably have zonal architecture defined frameworks, and then what do we understand by system level framework. There is a strong demand in the industry for software-defined vehicles. I'm actually driving a car which is less than a year old. It's not even an electrical car, it's a regular combustion engine. And I just recently got a very significant update on my ADAS system over here. So I had some first-hand experience of what it means that you have a fairly new car and get a very, very important update. I'm now able to, drive in Germany my car on the motorway, with up to 160 kilometers, automatically. I had to pay for it, but it was a very nice update, and that gives sort of an impression of what the future is going to bring with these SDV vehicles. So, they're SDV vehicles. What is driving it, and what is the industry transforming to? Well, we heard, that OTA is a factor. The vehicles are now connected to the grid. Autonomous driving, I was just telling you about this new feature. Electrification are some of the trends there. So there's a lot of changes ongoing, and that is the emerging need for more software-driven and higher software content vehicles. So software will account for 90% of the features in the future is the prediction. And let me show you what sort of the development on the different architectures were and where we are now with the zonal architectures. So, most of the cars which are driving around have already, these state where you have vehicle computers, domain fusion system, and the zonal architectures are currently, in the development for most of the OEMs that will be released soon. And that's the first step for the basis of the software-defined vehicle structures. So I have a picture here to describe that a little bit further, and show you that the classical car has in the range of 120 to 160 different ECUs all connected on a system. You see that here on the left-hand side, and the vision of a new architecture for software-defined vehicles is, some ADCs, very powerful because of, the acceleration in the hardware development, some zonal ECUs which are then taking care of the sensor signals there. And of course, it's going to be a stepwise approach, but the devices have far higher requirements on network capabilities and bandwidth. And that's the example I want to take here, what problem that can create, and how to solve that. So it's not only that the architecture is changing, it's also a way how the supply chain and the responsibilities are changing a little bit. So traditionally, the OEMs were doing EE and networking design, and then had the tier ones helping them out with the MCU design, and they also had a lot of software responsibility. Nowadays, there are some critical aspects where the OEMs want to take ownership again. Siemens just explained that, and the reason for that is often, also liability. So some of the key elements here are taken care of by the OEMs, and that's changing the infrastructure a little bit. In fact, there are certain measurements then, which do change, So we're, in a sense, active, the way that things, the hardware was, off the shelf, now in Zonal, the OEM already, defining that, still sort of off the shelf. And then in the centralized ECU, then is probably a bomb design from the OEM. And that goes to all the different functions, the software platforms and so on and so forth. So the software platform used to be AutoSoft Plastic. It's still an important factor. In some it's a mixture. And when it comes to the central ECUs, it's probably AutoSoft with adaptive and even new systems like Linux. So as I said, it goes through the whole thing. And also the network system in the car is changing significantly. What does remain is a few components. So, the increased number of features, need more functionalities. So the high compute ECUs are, using more and more software. And with that, there's pressure, of course, to get control, the costing control and have a fast implementation. We still rely on standards which have been proven in the industry and make sure that safety and security are not following up, and that's, for example, AutoSoft. And of course, then, the silicon industry is supplying multi-core devices, automotive qualified and all that, and is feeding that trend. So with that, I want to look a little bit on Ethernet now to describe a few problems we see in the zonal architecture when it comes to Ethernet connections. I can't move any further. Oh, here we go. Thank you. So, yeah, that's a complicated picture. I understand. I don't necessarily want you to understand the picture, but I just want to point out that Ethernet stack, has several design aspects. And you might think, well, Ethernet, we have that on the internet, we have that on our phones and all that, what's the problem? Well, there's certain requirements, which are specific to the automotive industry. And one of them is that you have to follow a standard. AutoSoft, for example, defines how Ethernet protocols are enabled. But then there are OEM requirements in addition to that. And sometimes there are requirements from a specific hardware. And, we just wanted to point out here, if you have a multi-core system and you want to do Ethernet, then that all gets already a little bit complicated. Just because AutoSoft, for example, defines that a Ethernet port is dedicated to one logical, CPU. And, that is different if you have multiple cores. You might distribute your applications actually to use both cores, and then there's inter-core communication required. You have different fibers, and it can get tricky. So you need to take care of that. Just one problem. Don't want to go into details of that problem. And here is another scenario, which again just shows, well, if you now have VLANs and need to again interact on different cores, similar problems. That's what the internet does not have, right? It's very specific to this environment. And again, the whole safety and security aspects. On the internet, if a package is not coming through, well, you might have a problem with your browser and all that, you refresh the site, all good. That's not the same or not tolerable in a car, just for reliability and safety reasons. So with that, what is the demand on the Ethernet? Well, you do want to describe that with different profiling managers. And I want to emphasize that there are different stacks out there, and you might have to look at different parameters to select the right one. So EC configuration and portability is one of the key criteria. And you want to make sure that the resources you have available are managed correctly so that they are in range. You want a simple and straightforward code base. That's always desirable. And you want to have simple architectures, which does support multi-core and partition support. Also not trivial to achieve. The implementation of different RFCs, and of course, execution. So with that, when you select a stack, you will come up with different categories. And then there are different stacks around, and you can select them. They probably also have different, advantages, like speed or whatever, but those probably do not fulfill all of the requirements. And, we just listed 2 examples there, where you have some features missing here, and, on the left-hand side, and others, being fulfilled on the right-hand side. So, it is important that you do some profiling and define exactly what kind of, network you want to supply. Another aspect are the different RFCs. So you might have a list of RFCs which are required, and that's just an example. And then, again, you have certain, stacks which do fulfill that, who partly fulfill it, and so on and so forth. So with your tasks of profiling, you then, look at your evaluation of the different stacks, and you group them in different categories. And then you have certain design considerations which have to be fulfilled. Those are the major ones. And you see a few examples here. So certain RFCs have to be fulfilled and all that. So basically, if the stack doesn't meet your major requirements, you have the problem that you cannot use that stack, and it is not a valid option. So, as I said, there are certain examples there. For example, certain VLAN aspects are not, there are certain RFCs are missing, then that does not. There are other considerations, like medium considerations, and you might want to, you consider that stack or can live with that stack. Those are, aspects where, for example, there are certain requirements missing, but you can replace them with other. The code compliance is not to the C8990 standard, only to the C11 standard, for example. Or you have problems with the checksum calculation. So these are examples where, you probably wish for, and you probably want to find a way to achieve these requirements anyway, but the stack can be considered. And then there are some low parameters where, they can typically be tolerated. It's more like documentation aspects and things like that. So you want to classify and you want to do some profiling of your Ethernet stacks. And then whatever stack you are then using, you want to make sure that that stack is then configured correctly, and you have a safe and secure network communication. And there are different aspects then required. And let me show you what we think a system-level approach should look like. So building a real-time SDV is not easy. So there are a lot of challenges. There are increasingly complex networks and increasingly complex zonal ECUs. And those new MCUs are not easy to program, not easy to configure. It's actually harder than if you have a simpler structure. Then there's, of course, also the burden that you need specialized experience for these complex functions and features. So that's a financial burden. You need to probably hire extra capacity. It's a complex and a design, and your existing tooling, might lack automation, and with that, it's getting complicated. The colleague from Bosch just outlined in the presentation before lunch how important it is to have system-level design. And then there's heavy dependency on physical testing. And my apologies for whatever reason, there is an animation missing there. We had some nice logo there for tooling. But yeah, these more complex systems need more and more testing, and that can increase cost and adds delays, particularly if you do that physically. So, another aspect is that modern engineering processes require a different kind of digital thread. So, you know the typical V cycle, and we have the change management reflected there. We actually think that we need to break that down into smaller V's, and we need to look at a V system for system levels, for the E architectures, for the electrical engineering, for software engineering, and for the mechanical engineering. With that way, you can act far more agile. And once you've done your system level design and verify that, it's a good approach into the next step, where if you would go the classical route, you would not really be through the V cycle after you've done the full software engineering. So if you break the 3 cycles down and have the right tooling for that, that will be sufficient and will make your system design faster and more efficient. And also much more changeable, because one of the key things is that SDVs should remain on the street for a longer period of time, and you want to be able to be flexible, do updates on mistakes, but also provide new features. So with that, we think that a EE system development should be seen as a holistic approach, where you have EE architecture design, the system design, then go into software architecture. You need to define your network, and then at the end you need to have your embedded solution. That's the AutoSAR base and the AutoSAR configuration and all the components around it. And if you think about it, if you make any changes to your network design or however you define your network design, it is also then having an impact on your electrical parameters. So your harness design and the connectivity is influenced by it. And ideally, the data is provided to the electrical design as well. Well, if we add to that a few components, and that is the application lifecycle management, the product lifecycle management. If you do requirement and system modeling impacts there, and if you do then a verification, particularly a digital verification, then you are what we like to call an approach where you have a digital twin of your design. So with this approach, we're suggesting here in the different toolings, you have a holistic way to define, in my case, or in my example, this Ethernet networking approach in a safe and secure way that is actually allowing you to do a much larger system-based design. And we can even, and it's desirable that this tooling is interacting with each other. That will help to, have your different functions in your company, so the different engineering aspects working, closely together with the same kind of tooling, and can interact with the information or can exchange the information very, very easily. And you can even then have third-party software, adapted to that or included to that, or provide the same information to your supply chain. I talked earlier about the OEMs are taking back more responsibilities, but they still need the tier 1 supply chain to provide the solutions, the hardware solutions, and build the hardware solutions at the end of the day. So, simplified, this three big blocks: system, software, and electrical. With the integration of the requirements, the application lifecycle, product lifecycle, and verification, manufacturing capabilities there is what we suggest, for those system design frameworks. With that, a quick summary and update. So, there's regular change going on in the automotive industry and landscape, and there's lots of opportunities there, but trends and features and linked to new technology, and it certainly will drive innovation. Zonal architectures is the industry trends and driving the change in the EE architectures. And with the EE architecture change, that is consolidating then, functionality and goals. OEMs are taking ownership of IP, and the software constraint, is with high compute ECU powers less and less a factor. Ethernet is the enabler of architectures. That's the communication backbone. That's pretty much, decided already and implemented to a large extent. It's based then on a lot of standards, like OpenSOF, for example. But there's always extensions required and necessary, and reference designs are then required. And the system level framework, so additional threat, for an ECU software development, can help to enable, SDVs and have a total solution then, which is flexible and comprehensive for, the various functions in a company, in OEM, and so on. And then my last slide here, Siemens is offering a solution which is called Accelerator. That is also offering the AutoSOC package in that solution and the configuration tools. Everything what I showed you in the earlier slides is part of our Accelerator portfolio. So you can build a comprehensive twin. The whole solution is very, very customizable. And it's a flexible system. It's open to integrate other components. For example, Rhapsody from IBM can be interfaced to that, or the MacWorks tooling is interfacing to that. And the approach is that you have a digital twin. You can verify that digitally, so you don't need to wait for your hardware, and you can even do that in the cloud. So we have web-based computing as well as computing on a local machine. And the data can also be exchanged over the web, which helps again speed up the process, and that will be more and more important in the future. With that, I thank you very much for your attention, and I'm happy to answer any questions if you have any.
Thank you. So we have time. So if you have any question, okay, I'll come.
Thank you for the presentation. I have a question. In one of your slides where you mentioned some of the risks and you classified as high, medium, and small. I saw under the high risk category you mentioned PCP not present on the TX as a risk on Fluidilab. Can you elaborate more on what is the risk that you anticipate there?
Well, it is typically a important parameter for safety and security. Now, if the VLAN is not handled correctly and in the expected way, that was, I guess, an earlier approach, particularly for multi-cores. You have the problem that your firewalls are not working correctly and so on and so forth. So that is a risk. It's not necessarily for all the applications, right? But I'm saying it could be a requirement, and often it is. That's what I tried to elaborate in one of the pictures there, and then you know, it is a major factor.
Thank you.
Sure.
Thank you very much. Any other question? It's okay?